For centuries, astronomers believed they understood how planets form. Gas giants orbit far from their stars, where it's cold enough for ice and gas to accumulate. Rocky worlds stay close, where temperatures vaporize volatile materials. Small planets circle dim stars, massive ones orbit bright ones. The rules seemed simple, written into the physics of stellar formation itself. Then we started finding planets that break every single rule. Gas giants scorching in orbits closer to their stars than Mercury is to our Sun, completing years in mere days. Rocky super-Earths are larger than anything in our solar system. Planets orbiting where theory says nothing should exist at all. These worlds shouldn't be possible according to our models of planetary formation. Yet they're out there, circling distant stars, challenging everything we thought we knew about how solar systems work. Welcome to the universe's most confusing neighborhoods, where the impossible happens and physics gets weird. The hot Jupiter problem. Jupiter orbits the Sun at a comfortable distance of about 5 astronomical units, taking nearly 12 years to complete one trip around our star. That's exactly where planetary formation models predict gas giants should form, in the cold outer regions of a stellar system where temperatures drop low enough for water to freeze into ice. This ice becomes the foundation for building massive worlds. Dust grains stick together, forming pebbles. Pebbles accumulate into boulders. Boulders merge into planetesimals. Once these cores reach about 10 Earth masses, their gravity becomes strong enough to pull in enormous envelopes of hydrogen and helium from the surrounding nebula. The process requires cold temperatures, abundant material, and millions of years. Gas giants, according to this well-tested theory, simply cannot form close to their stars. Then in 1995, astronomers Michel Mayor and Didier Queloz discovered 51 Pegasi b, and everything changed. This planet, later nicknamed Bellerophon, is a gas giant roughly half the mass of Jupiter, but it orbits its star at just 0.05 astronomical units. That's 8 times closer than Mercury orbits our Sunday. Instead of taking years to orbit, 51 Pegasi b completes a full revolution in just 4.2 days. Its atmosphere, heated to over 1,000 degrees Celsius by its star's intense radiation, glows bright enough to be detected directly. The discovery shocked the astronomical community. This planet existed in a place where gas giants weren't supposed to survive, let alone form. The temperature at 51 Pegasi b's orbital distance would have exceeded 1,500 Kelvin during the system's formation, far too hot for ice to exist. Without ice, there's no foundation for building the massive solid cores needed to capture gas. The hydrogen and helium that make up most of the planet's mass would have been blasted away by the young star's intense radiation and stellar wind before a core could grow large enough to hold it. Every model of planetary formation said this world couldn't exist where we found it, yet there it was, orbiting like clockwork, completely indifferent to our theories. Scientists quickly realized that 51 Pegasi b must have formed much farther from its star, beyond the ice line where conditions were right for gas giant formation, and then migrated inward. But that explanation raised more questions than it answered. What could cause a massive planet to spiral inward across billions of kilometers? The answer lies in the protoplanetary disk, the swirling cloud of gas and dust surrounding young stars. As a young Jupiter-sized planet orbits within this disk, its gravity creates waves and disturbances in the surrounding material, like a boat moving through water. These waves carry angular momentum, transferring it from the planet to the outer disk and from the inner disk to the planet. The net effect pushes the planet inward through a process called Type II migration. Computer simulations showed this migration could be rapid. A gas giant forming at 5 astronomical units could spiral all the way down to 0.05 astronomical units in less than 100,000 years, a blink of an eye in cosmic terms. The planet would continue falling inward until something stopped it. In many cases, that stopping point is the star's magnetospheric cavity, a region where the stellar magnetic field clears out the inner disk, creating a barrier. Other planets might be halted by gravitational interactions with additional planets in the system or by gaps they carve in the disk itself. Following the discovery of 51 Pegasi b, hundreds more hot Jupiters have been found. Surveys like the Kepler mission revealed that roughly 1% of Sun-like stars host these scorching gas giants. WASP. 1-2b orbits even closer, just 0.023 astronomical units from its star, with surface temperatures exceeding 2,500 Kelvin, hot enough to vaporize iron. The planet is so close that its star's gravity is literally tearing it apart, stretching it into an elongated shape and stripping away its outer atmosphere at a rate of about 6 billion kilograms per second. Within 10 million years, the planet will be completely consumed. The discovery of hot Jupiters also explained a mystery in our own solar system. For decades, astronomers had wondered why the inner solar system contained only small, rocky planets. Computer models of the early solar system suggested Jupiter might have migrated inward to roughly 1.5 astronomical units before reversing course and moving back out, a phenomenon called the grand tack. This inward, then outward migration would have scattered or ejected any larger planets forming in the inner system, leaving only the rocky worlds we see today. The evidence for this migration includes the asteroid belt's truncated mass and the compositional differences between Earth and Mars. Hot Jupiters remain among the most intensively studied exoplanets because they're relatively easy to detect and observe. Their large sizes create deep transit signals when they pass in front of their stars, and their short orbital periods mean these transits repeat frequently. This makes them ideal laboratories for studying atmospheric composition, weather patterns, and the effects of extreme stellar radiation on planetary atmospheres. Spectroscopic observations have detected sodium, potassium, water vapor, carbon monoxide, and even titanium oxide in hot Jupiter atmospheres, chemicals that tell us about temperatures, winds, and cloud formation on these alien worlds. Planets orbiting dead stars. White dwarfs are stellar corpses, the compressed remnants left behind when sun-like stars exhaust their nuclear fuel and collapse. These objects pack roughly the Sun's mass into a sphere the size of Earth, creating surface gravities 100,000 times stronger than Earth's. Their formation process is violent. As a star runs out of hydrogen, it swells into a red giant, expanding to hundreds of times its original size. This expansion engulfs and vaporizes any planets orbiting within about 5 astronomical units. The star then ejects its outer layers in a planetary nebula, exposing the hot, dense core that becomes a white dwarf. Any planetary system surrounding such a star should be utterly destroyed by this transformation. Yet we've found planets orbiting white dwarfs, somehow surviving catastrophes that should have obliterated them. The first hints came in the 1990s when astronomers detected excess infrared emission from white dwarfs, a signal indicating the presence of warm dust in tight orbits around these stellar remnants. Detailed observations revealed this dust was rich in heavy elements like iron, silicon, and magnesium, the building blocks of rocky planets. Spectroscopic studies of white dwarf atmospheres showed something even more remarkable. About 25 to 50% of white dwarfs have atmospheres polluted with these same heavy elements. Since white dwarfs have extremely strong surface gravity, heavy elements should sink out of their atmospheres in less than 1 million years. Their presence meant something was actively delivering rocky material to these stars essentially. The white dwarfs were eating planets. In 2020, astronomers discovered the first intact planet orbiting a white dwarf. WD 1000 856 plus 534b, is a gas giant roughly the size of Jupiter, orbiting its white dwarf host at just 0.02 astronomical units, much closer than Mercury orbits the Sunday. The planet completes one orbit every 1.4 days. Its existence poses an immediate problem. How did it survive? When WD 1856 plus 534 was a normal star, it would have swelled into a red giant, with a radius larger than the planet's current orbital distance. The planet should have been swallowed and destroyed. The most likely explanation is that the planet originally formed much farther out and migrated inward after the star became a white dwarf. But this migration would have required gravitational interactions with other planets in the system, planets that might have been destroyed in the process, with their remains now forming the dusty debris disks we observe. Another system, WDJ 914 plus 1000, 914, revealed an even stranger scenario. Astronomers detected an evaporating planetary fragment orbiting the white dwarf every 2 hours at a distance of just 0.005 astronomical units, about 750,000 kilometers. or roughly twice the distance from Earth to the Moon. The object is losing mass at about 3,000 kilograms per second as the white dwarf's intense radiation and tidal forces tear it apart. Spectroscopic observations showed the vaporized material contained high concentrations of iron, suggesting this fragment is the exposed core of a destroyed planet, possibly similar to Mercury, which has an unusually large iron core relative to its size. The pollution of white dwarf atmospheres tells us that planetary destruction around these stellar remnants is common and ongoing. Current models suggest the process works like this. When a star becomes a white dwarf, gravitational interactions among surviving planets become chaotic because the central star's mass loss during the red giant phase weakens its gravitational control over the outer system. Planets scatter each other onto highly eccentric orbits. Some planets are ejected from the system entirely. Others plunge inward toward the white dwarf. As they approach, tidal forces, the difference in gravitational pull between the planet's near and far sides, rip them apart, creating streams of rocky debris. This debris forms a disk around the white dwarf, gradually spiraling inward and contaminating the star's atmosphere with heavy elements. Studies using the Hubble Space Telescope and ground-based observatories have detected gaseous debris disks around several white dwarfs. These disks contain vaporized rock silicon, magnesium, calcium, and iron in gaseous form, orbiting at temperatures exceeding 1000 Kelvin. The disks are incredibly thin, just a few hundred kilometers thick, maintained by the balance between gravity pulling material inward and radiation pressure pushing it outward. Material from these disks rains down onto the white dwarf's surface at rates of up to 1 billion kilograms per second, continuously polluting the stellar atmosphere. Detailed chemical analyses of polluted white dwarf atmospheres have revealed something remarkable. The compositions of the accreted material closely match rocky planets and asteroids. Some white dwarfs show evidence of water-rich material, suggesting they've consumed objects similar to icy asteroids or comets. Others show ratios of elements matching Earth's mantle composition. A few show evidence of crustal material, the outermost layer of differentiated rocky bodies. These observations provide a unique way to study the interiors of exoplanets. While we can only observe the surfaces and atmospheres of planets around living stars, white dwarfs that have consumed planets give us direct spectroscopic measurements of their interior compositions. The discovery of planets and planetary debris around white dwarfs has implications for the future of our own solar system. In about 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, likely engulfing Mercury, Venus, and possibly Earth. Mars and the outer planets should survive this phase, but the Sun's mass loss will weaken its gravitational grip on these worlds. Their orbits will expand, and gravitational interactions among them may become chaotic. Some might be ejected into interstellar space. Others could spiral inward toward the white dwarf that was once our Sun, eventually being torn apart and scattered across the stellar surface, the final chapter in their 4 billion year existence. Rogue planets drifting between stars. Most planets orbit stars. That's the definition we've used for thousands of years. Planets are wanderers, yes, but wanderers bound by gravity to follow predictable paths around stellar masters. But scattered throughout the galaxy are worlds that follow no star at all. These rogue planets drift through interstellar space, frozen and dark, untethered from any solar system. They shouldn't exist in large numbers. Planet formation requires the material and gravitational environment provided by a protoplanetary disk around a young star. Yet surveys suggest there could be billions of these orphaned worlds floating in the darkness between stars, outnumbering ordinary planets by a significant margin. The first strong evidence for rogue planets came from gravitational microlensing surveys. This technique relies on Einstein's general relativity, which predicts that massive objects bend spacetime, acting as gravitational lenses. When a rogue planet drifts between Earth and a distant star, its gravity briefly magnifies the star's light, creating a characteristic brightening curve that lasts hours to days depending on the planet's mass and speed. Unlike transit observations that require planets to pass directly in front of their stars, microlensing works for planets anywhere in the galaxy, including those floating freely through space. Between 2006 and 2020, microlensing surveys detected dozens of candidate rogue planets, with masses ranging from Earth-size to several times Jupiter's mass. Statistical analyses of these detections suggested there could be 2 rogue planets for every star in the Milky Way, a staggering population exceeding 400 billion worlds. Later observations refined these estimates, but even conservative models suggest rogues are common. Some may be true orphans, ejected from their birth systems during chaotic early interactions. Others might be extremely distant members of planetary systems, orbiting their stars at thousands of astronomical units so far out that detecting their orbital motion is nearly impossible. The formation mechanisms for rogue planets fall into 3 main categories. The first involves gravitational ejection. Computer simulations of young planetary systems show that multi-planet configurations are often unstable. When 3 or more planets form with certain orbital configurations, gravitational interactions can amplify over millions of years, eventually flinging 1 or more planets out of the system at velocities exceeding the star's escape velocity. This process is particularly efficient in systems with massive gas giants, where the gravitational perturbations are strongest. Studies suggest that most planetary systems eject at least 1 planet during their early evolution, making ejected rogues potentially the most common type. The second mechanism involves disrupted planetary systems. When stars form in dense clusters, close encounters with other stars or the cluster's overall tidal forces can strip planets from their orbits. A star passing within a few hundred astronomical units of another stellar system can gravitationally perturb planets, sending them into highly eccentric orbits or ejecting them entirely. This process might be especially common in the crowded environments where most stars form. Observations of young star clusters show evidence of disrupted protoplanetary disks, supporting this scenario. The third mechanism is the most controversial: direct formation in interstellar space. Some theoretical models suggest that the densest regions of giant molecular clouds, the vast, cold nebulae where stars form, could fragment into clumps with planetary masses. These clumps would collapse under their own gravity, forming planet-like objects that never orbit a star. Observations have detected very low-mass objects in star-forming regions that appear to be free-floating, but determining whether they formed like planets or like stars remains challenging. The dividing line between a rogue planet and a brown dwarf, a failed star too small to sustain hydrogen fusion, is blurry and depends on formation mechanism rather than just mass. One of the most intriguing discoveries involves young rogue planet candidates in nearby star-forming regions. In the Orion Nebula cluster, observations with the Hubble Space Telescope identified dozens of free-floating planetary mass objects with masses between 5 and 15 times Jupiter's mass. Some show evidence of surrounding disks miniature versions of protoplanetary disks, raising questions about whether these objects could form their own satellite systems. If rogue planets can retain moons, those moons might experience tidal heating similar to Jupiter's moon Io, potentially creating subsurface liquid water oceans, even in the frigid darkness of interstellar space. The dynamics of rogue planets raise additional questions. Do they remain in the galaxy's disk, where they formed, or do some escape into the galactic halo? Velocity measurements from microlensing events suggest most rogues travel at speeds similar to stars in the galactic disk, implying they haven't been ejected with extreme velocities. But a small fraction might achieve escape velocity from the galaxy entirely, becoming intergalactic wanderers destined to drift through the void between galaxies for trillions of years. These cosmic nomads would represent the ultimate isolation worlds forever separated from stars, galaxies, and any possibility of detection. The study of rogue planets is entering a new era with next-generation telescopes. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will conduct extensive microlensing surveys capable of detecting Earth-mass rogue planets. These observations will provide the first reliable census of free-floating worlds, answering fundamental questions about their abundance, mass distribution, and formation mechanisms. If rogues are as common as current estimates suggest, they represent a major component of the galaxy's planetary population, a hidden cosmos of dark, frozen worlds far outnumbering the illuminated planets we've focused on until now. Super-Earths that challenge formation models. Our solar system contains a clear division. Close to the Sun orbit 4 small rocky planets with masses between 0.055 and 1 Earth masses: Mercury, Venus, Earth, and Mars. Beyond the asteroid belt lie 4 gas and ice giants with masses between 14.5 and 318 Earth masses: Neptune, Uranus, Saturn, and Jupiter. There's nothing in between. No intermediate-sized planets with masses between 2 and 10 Earth masses exist in our cosmic neighbourhood. For decades, astronomers assumed this arrangement was typical. Then we started surveying other solar systems and discovered that our system is a weird one. The most common type of planet in the galaxy is one completely absent from our solar system, the super-Earth. Super-Earths are planets with masses between approximately 2 and 10 times Earth's mass. Surveys from the Kepler mission revealed that roughly 30 to 50% of Sun-like stars host at least one super-Earth, making them the most abundant class of exoplanet. Many orbit closer to their stars than Mercury orbits the Sun, completing full revolutions in days or weeks. Their existence challenges our understanding of planetary formation because our solar system's architecture suggests such planets either shouldn't form or shouldn't remain in close orbits. Yet there they are, thousands of them, orbiting other stars in configurations that our models struggle to explain. The composition of super-Earths adds another layer of mystery. Because we can't directly sample their interiors, astronomers infer composition from mass and radius measurements. A planet's density, its mass divided by its volume, provides crucial clues. A low-density super-Earth likely contains significant amounts of hydrogen and helium, making it a mini-Neptune. A high-density one is probably rocky, with an iron core and silicate mantle similar to Earth. The transition between these two types occurs around 1.6 Earth radii. Planets smaller than this tend to be rocky. Planets larger tend to be gaseous. This boundary, called the radius valley, suggests a fundamental transition in how planets form or evolve. One explanation for the radius valley involves atmospheric loss. Planets forming with substantial hydrogen-helium atmospheres can lose these envelopes through several mechanisms. Young stars emit intense ultraviolet radiation and stellar winds that can strip away gaseous atmospheres, especially from smaller planets with weaker gravity. This process, called photoevaporation, might erode mini-Neptune envelopes down to rocky cores over hundreds of millions of years, creating the observed population of bare super-Earths. Supporting this idea, observations show that planets straddling the radius valley often orbit active, young stars, where photoevaporation would be strongest. Another mechanism involves core-powered mass loss. As a planet's molten core cools and solidifies, it releases enormous amounts of energy. This heat can drive atmospheric escape from below, pushing gas into space even without external radiation. Models suggest this process could strip the atmospheres from planets with cores around 5 Earth masses, leaving behind dense rocky super-Earths. The relative importance of photoevaporation versus core-powered loss remains debated, with different studies favouring different mechanisms depending on the stellar and planetary properties considered. The formation location of super-Earths presents yet another puzzle. Did they form where we find them close to their stars, or did they migrate inward from more distant birthplaces? If they formed in situ, the protoplanetary disk must have contained enormous amounts of solid material close to the star, far exceeding what models predict. The inner regions of protoplanetary disks are hot, with temperatures exceeding 1,500 Kelvin within 0.1 astronomical units of Sun-like stars. At these temperatures, rocky materials can barely condense from vapor, making it difficult to accumulate enough solid material to build multiple super-Earths. Yet Kepler found systems with 3, 4, even 6 super-Earths, all orbiting within this hot inner zone. Migration offers an alternative. Super-Earths could form farther out, where temperatures are lower and solid material more abundant, then spiral inward through interactions with the gaseous disk. This inward migration would naturally pack planets into tight configurations as they pile up at the disk's inner edge. But migration introduces its own problems. Why would migration stop before the planets plunge into the star? What determines how many planets participate in migration versus remaining in distant orbits? And why does our solar system apparently lack this entire population of migrated super-Earths? The Grand Tack hypothesis offers one answer for our solar system's peculiarity. This model proposes that Jupiter formed early and migrated inward to about 1.5 astronomical units before reversing course and migrating back outward a tack in sailing terms. This inward then outward journey would have scattered or ejected any forming super-Earths, preventing their survival in the inner solar system. The reversal might have been triggered by Saturn's formation, which locked both gas giants into a gravitational resonance that reversed their migration. This would make our solar system atypical, a rare case where gas giant migration occurred and then reversed, rather than continuing until halted by the star's magnetosphere. Observational tests of these formation scenarios focus on super-Earth atmospheres. Transmission spectroscopy observing starlight filtering through a planet's atmosphere during transits can reveal atmospheric composition. Several super-Earths show evidence of hydrogen-rich atmospheres, indicating they're actually mini-Neptunes rather than scaled-up rocky worlds. Others show no detectable atmosphere, suggesting they're bare rocky cores. A few show spectroscopic signatures of water vapor, but whether this water exists as surface oceans, atmospheric humidity, or chemically bound in minerals remains unclear. Planets orbiting binary stars. Tatooine, the desert world from Star Wars that orbits two suns, was long considered pure science fiction. Astronomers thought planets couldn't form in binary star systems because gravitational perturbations from two stars would prevent the accumulation of planetary building blocks. The competing gravitational pulls would stir up material in the protoplanetary disk, accelerating collisions to destructive velocities and preventing planetesimals from growing. Even if planets somehow formed, their orbits would be unstable, leading to ejection or collision. Then, in 2011, NASA's Kepler mission detected Kepler 1.6b, Saturn-sized planet orbiting two stars in a configuration nearly identical to the fictional Tatooine. The discovery proved that not only can planets form around binary stars, but they might be relatively common. Kepler 1.6b orbits both of its stars at a distance of 0.7 astronomical units, taking 229 days to complete one orbit. The two stars themselves orbit each other every 41 days at a separation of just 0.22 astronomical units. From the planet's surface, observers would see two suns moving through the sky together, periodically eclipsing each other, one a K-type orange dwarf, the other a small, dim red dwarf. The system's geometry creates a complex gravitational environment where the planet experiences constantly varying tidal forces as the binary stars orbit their common center of mass. The planet's existence contradicts earlier theories in several ways. First, the circumbinary orbit, the path around both stars, lies dangerously close to the stability limit. Computer simulations show that planets orbiting closer than about 3 times the binary separation typically become unstable within millions of years, either colliding with one of the stars or being ejected from the system. Kepler 1.6b orbits at 3.1 times the binary separation, just barely stable. This narrow margin suggests either extraordinary luck or that planet formation around binaries naturally produces planets right at the stability boundary. Second, the formation environment should have been hostile. The two stars' orbital motion would have created powerful gravitational torques in the circumbinary disk, pushing material around and heating it through friction. This stirring would accelerate the relative velocities of dust grains and planetesimals, making collisions more destructive than constructive. Instead of sticking together to build planets, particles should have shattered on impact, grinding each other down to dust. Yet Kepler 1.6b formed despite these obstacles, implying that planet formation is more robust and adaptable than models suggested. Following Kepler 1.6b's discovery, Kepler found dozens more circumbinary planets, revealing that roughly 10% of close binary stars host detectable planets. These systems show consistent patterns. Most circumbinary planets are gas giants or sub-Neptunes with sizes between 3 and 12 Earth radii. Very few rocky planets have been found, possibly because smaller planets are harder to detect rather than truly absent. Nearly all orbit near the stability limit, between 3 and 5 times the binary separation. This clustering suggests a formation mechanism that preferentially places planets at specific distances. Current models propose that circumbinary planets form farther out in the disk, where gravitational perturbations are weaker, then migrate inward until reaching the stability boundary. As the planet migrates through the disk, interactions with gas transfer angular momentum, causing the planet to spiral toward the binary. But the binary star's gravity creates a cleared region, a gap in the disk, where their gravitational influence prevents gas from accumulating. When the migrating planet reaches this gap's outer edge, it encounters a sharp density transition. The lack of disk material ahead halts further inward migration, parking the planet just beyond the stability limit. This mechanism naturally explains why circumbinary planets cluster at similar relative distances across different systems. Another remarkable system is Kepler 4.7, which contains two circumbinary planets, the only known example of a multi-planet circumbinary system. The inner planet, Kepler 4.7b, is about 3 times Earth's radius and orbits every 49 days. The outer planet, Kepler 4.7c, is slightly larger than Neptune and orbits every 303 days within the binary's habitable zone. Later observations added a third planet, Kepler 4.7d, orbiting between the other two. The existence of 3 planets in stable orbits around a binary star pushes the boundaries of what gravitational dynamics should allow. The planets must maintain precise orbital configurations to avoid destabilizing resonances. Any significant deviation would lead to chaotic interactions and eventual ejection. Binary stars come in various configurations, and not all are equally hospitable to planets. Tight binaries, with orbital periods of days to weeks and separations less than 0.1 astronomical units, create the harshest environments. Wide binaries with separations of hundreds or thousands of astronomical units behave almost like independent stars, each potentially hosting its own planetary system. The intermediate range binaries separated by 1 to 50 astronomical units presents the most complex dynamics. Stars at these separations strongly influence each other's planetary zones, while remaining distinct enough to create complicated gravitational fields. In addition to circumbinary planets that orbit both stars, some binary systems host circumstellar planets that orbit just one star, while the companion orbits farther away. Alpha Centauri, the Sun's nearest stellar neighbour, is a binary system with a third, distant red dwarf companion, Proxima Centauri. Proxima hosts at least 2 confirmed planets, including Proxima b, a roughly Earth-mass world orbiting in the habitable zone. The main binary pair Alpha Centauri A and B might also host planets, though none have been confirmed yet. The system's complexity illustrates how planets can exist in multiple configurations within binary and multiple star systems. The habitability of circumbinary planets raises intriguing questions. Planets like Kepler 4.7c orbit in the habitable zone, where stellar radiation could maintain liquid water on the surface. But the double star configuration creates complications. The planet receives varying amounts of radiation as the 2 stars orbit each other, eclipse each other, and change their combined distance from the planet due to the binary orbit's ellipticity. These variations could drive complex climate cycles, seasonal patterns, not based on orbital position but on the binary star's relative configuration. Atmospheric and climate models are only beginning to explore how life might adapt to such environments. Ultra-short period planets. Most planets take at least several days to orbit their stars. Mercury, the fastest planet in our solar system, completes an orbit in 88 days. That seemed like a fundamental limit to get much closer, and tidal forces would tear a planet apart or cause it to spiral into the star. Then astronomers started finding planets that orbit their stars in less than 1 day. These ultra-short period planets, or USPs, complete years in mere hours, racing around their stars at such close range that their surfaces glow red-hot and their rocks begin to vaporize. They shouldn't survive tidal forces, and stellar radiation should have destroyed them long ago. Yet hundreds exist, defying our predictions and forcing us to reconsider what planetary systems can look like. The first ultra-short period planet, Corot 7b, was discovered in 2009. This world orbits its star every 20.4 hours at a distance of just 0.017 astronomical units, roughly 2.5 million kilometers, or about 6 times the Earth-Moon distance. The planet's dayside temperature exceeds 2,500 Kelvin, hot enough to melt rock and create a magma ocean. The planet is tidally locked, always showing the same face to its star, just as the Moon always shows the same face to Earth. This creates an extreme temperature gradient. The dayside is a furnace of molten rock, while the night side might be cold enough for rock to solidify. The formation of ultra-short period planets presents multiple challenges. Planets cannot form this close to their stars because the protoplanetary disk would be too hot for solid material to condense. Temperatures at 0.017 astronomical units exceed 2000 Kelvin, well above the vaporization point of rocky materials. This means USPs must have formed farther out and migrated inward. But what could cause such extreme inward migration, and why would it stop at such perilously close distances rather than continuing all the way into the star? One migration mechanism involves interactions with other planets. In multi-planet systems, gravitational perturbations can scatter planets onto highly eccentric orbits. When a planet on an eccentric orbit passes close to its star, tidal forces circularize the orbit, converting orbital energy into heat and causing the planet to settle into a close, circular orbit. But this process has limits. If the orbit is too close, tidal forces from the star raise enormous tidal bulges on the planet. The star's gravity pulls harder on the near side than the far side, creating internal friction that converts the planet's rotational and orbital energy into heat. This energy loss causes the orbit to decay, the planet spirals inward until it either stabilizes or plunges into the star. The survival of ultra-short-period planets depends on a delicate balance. Tidal forces cause orbital decay, but this decay rate depends on the planet's internal structure. Rocky planets with rigid interiors dissipate tidal energy slowly, allowing them to survive in close orbits for billions of years. Planets with significant molten layers or thick gaseous envelopes dissipate energy more efficiently, leading to faster orbital decay and eventual destruction. Observations show that nearly all ultra-short-period planets are rocky. No gas giants exist at these extreme distances. This supports the idea that only solid rocky worlds can survive so close to their stars. K2 141b exemplifies the extreme conditions on USPs. This planet orbits its star every 6.7 hours at 0.007 astronomical units, closer than any other known rocky planet. Its dayside temperature exceeds 3000 Kelvin, hot enough to vaporize rock into a thin atmosphere. Models predict the planet's surface is entirely molten, a global magma ocean hundreds of kilometers deep. The extreme temperature drives a rock vapor cycle similar to Earth's water cycle. Rock evaporates on the dayside. Winds carry the vapor to the night side where it condenses and rains down as liquid rock, then flows back to the dayside through lava rivers to evaporate again. Another ultra-short-period planet, TOI 561b, is one of the oldest known rocky planets at approximately 10 billion years old, more than twice Earth's age. Despite its extreme orbit at 5-hour period, at 0.01 astronomical units, the planet has survived for billions of years, demonstrating that these configurations can remain stable over vast timescales. The planet's low density, about half Earth's, suggests an unusual composition, possibly with a larger fraction of light elements like calcium and aluminum compared to Earth's iron-rich interior. Statistical studies reveal that ultra-short-period planets are relatively rare, appearing around only about 0.5% of Sun-like stars. This rarity contrasts with hot Jupiter's 1% and super-Earth's 30 to 50%, suggesting that the formation or survival of USPs requires special circumstances. Interestingly, most USPs are found in multi-planet systems, often accompanied by additional planets at larger orbital distances. This pattern supports the planet-planet scattering scenario, where gravitational interactions among multiple planets inject one onto an extreme orbit while leaving others in more conventional configurations. The extreme stellar radiation USPs receive has another consequence: atmospheric erosion. X-ray and ultraviolet radiation from the star heats the planet's atmosphere or vaporized rock envelope, causing it to expand. If the atmosphere's scale height, the altitude over which atmospheric pressure decreases significantly, becomes comparable to the planet's radius, material at the top of the atmosphere can reach escape velocity and stream away into space. This process, called thermal escape or atmospheric blow-off, should gradually strip away the planet's atmosphere and perhaps even erode the surface layers over time. Observations support this scenario. Several ultra-short-period planets show evidence of ongoing mass loss through cometary-like tails of escaping gas. K2 22b, also known as KIC1 1442 793, exhibits transits that are asymmetric. The transit depth and shape change from one orbit to the next, suggesting a variable cloud of debris surrounding the planet. This debris likely consists of dust grains ejected from the planet's surface by intense stellar radiation, creating a dynamic, evolving environment around the planet. The long-term fate of ultra-short-period planets is grim. Tidal orbital decay will eventually cause them to spiral into their stars, though the timescale depends on specific planetary and stellar properties. For most systems, this process takes billions to tens of billions of years longer than the current age of the universe. But for the closest USPs, orbital decay might occur within a few billion years, representing a transient phase in planetary system evolution. We may be observing these planets during a brief window when they're visible before they disappear into their stars, leaving no trace of their existence. Planets in the habitable zone of extreme stars. The habitable zone is the range of orbital distances where a planet receives enough stellar radiation to maintain liquid water on its surface, not so close that water boils away, not so far that it freezes solid. For Sun-like stars, this zone extends roughly from 0.95 to 1.37 astronomical units. Earth orbits comfortably within it, receiving just the right amount of warmth. Astronomers long assumed that habitable zones around other types of stars would follow similar principles, scaled by stellar luminosity. But as we've discovered planets around extreme stars, ultra-cool dwarfs, red giants, and even white dwarfs, we've found that habitability depends on far more than just temperature. Planets in these zones face challenges we never anticipated: tidal locking, stellar flares, extreme ultraviolet radiation, and rapid changes in stellar output that make the concept of a habitable zone far more complex than a simple temperature range. Ultracool dwarf stars, red dwarfs smaller and cooler than the Sun, are the most common stars in the galaxy, comprising about 70% of all stars. Their low luminosity means their habitable zones lie very close in, typically between 0.02 and 0.2 astronomical units. At these distances, planets orbit in days rather than years, and tidal forces from the star quickly lock the planet's rotation to its orbit. This synchronous rotation means one side of the planet perpetually faces the star, while the other remains in eternal darkness, a configuration that creates extreme climate challenges. But tidal locking introduces another problem: atmospheric collapse. If a planet's atmosphere is too thin, the night side becomes so cold that gases freeze out, falling to the surface as ice. This process removes atmosphere from circulation, eventually depositing most of it on the night side as frozen lakes of nitrogen, oxygen, or carbon dioxide. The day side, devoid of atmospheric pressure, would resemble the Moon, airless and barren despite being warm enough for liquid water. Recent climate models suggest this outcome is likely for planets around the coolest red dwarfs unless volcanic activity or other processes continuously replenish the atmosphere. Red dwarf stars present another hazard: stellar flares. Young red dwarfs are extremely active, producing powerful flares that can temporarily increase their luminosity by factors of 10 or more. These flares emit intense ultraviolet and X-ray radiation that can strip away planetary atmospheres through a process called photoevaporation. Proxima Centauri b, an Earth-mass planet orbiting in the habitable zone of the Sun's nearest stellar neighbour, receives flare radiation 500 times more intense than Earth receives from the Sunday. Over billions of years, this bombardment could have stripped away any primordial atmosphere, leaving the planet airless and lifeless. Though if the planet retains significant volcanic activity or possesses a strong magnetic field, it might maintain an atmosphere against this erosion. At the other extreme are planets around dying stars. As sun-like stars exhaust their hydrogen fuel, they expand into red giants, swelling to hundreds of times their original size. This expansion engulfs and destroys any planets in close orbits, including those initially in the habitable zone. But as the star's radius increases, so does its luminosity by factors of thousands, pushing the habitable zone outward to several astronomical units. Planets that were once frozen ice worlds beyond the habitable zone suddenly find themselves in the temperate zone, receiving enough warmth for liquid water. The red giant phase lasts only about 1 billion years before the star sheds its outer layers and contracts into a white dwarf. During this brief window, previously frozen moons and planets could experience warm conditions. Saturn's moon Titan, currently a frigid world with surface temperatures around 94 Kelvin, would warm dramatically, potentially melting its ice crust and exposing subsurface liquid water oceans. Jupiter's moon Europa, thought to harbour a subsurface ocean beneath its icy shell, might develop surface oceans. These thawed worlds would remain habitable only temporarily, cooling again once the star becomes a white dwarf, but a billion years is enough time for life to emerge, if Earth's history is any guide. White dwarfs themselves have habitable zones, though these zones are incredibly close, typically between 0.005 and 0.02 astronomical units. At these distances, orbital periods are just hours to days. The first planet discovered in a white dwarf's habitable zone, WD 1000, 856 plus 534b, orbits at 0.02 astronomical units with a 1.4-day period. While this gas giant is not itself habitable, if it hosts large moons similar to Jupiter's Galilean satellites, those moons would receive stellar radiation comparable to what Earth receives from the Sun, at least in terms of total energy, though the radiation spectrum would be shifted toward ultraviolet wavelengths due to the white dwarf's high surface temperature. The challenge for white dwarf habitable zones is stellar evolution. White dwarfs cool over time, gradually dimming and shifting their habitable zones inward. A planet initially in the habitable zone will eventually freeze as the star cools, becoming uninhabitable within a few billion years. This places a time limit on habitability around white dwarfs shorter than the several billion-year timescale life took to develop on Earth, though possibly long enough for simpler ecosystems. Recent discoveries have found planets around rapidly rotating massive stars, though none yet in the habitable zone. These systems face unique challenges. The intense ultraviolet radiation from hot stars would dissociate water molecules in planetary atmospheres, splitting them into hydrogen and oxygen. The light hydrogen escapes to space while the oxygen might accumulate, creating oxidizing atmospheres very different from Earth's. Additionally, massive stars emit powerful stellar winds, particle outflows far more intense than the solar wind that could erode atmospheres even of planets with strong magnetic fields. The concept of the habitable zone continues to evolve as our understanding deepens. Traditional definitions based solely on surface temperature are giving way to more nuanced models, incorporating atmospheric composition, tidal heating, magnetic fields, and stellar variability. Some researchers propose expanding the definition to include subsurface habitability, where life might exist in underground oceans warmed by tidal heating or radioactive decay, independent of surface conditions. If we accept this broader definition, habitable zones extend much farther, potentially to planets and moons orbiting far from their stars, or even to rogue planets drifting through interstellar space. Evaporating planets losing their atmospheres. Planets are supposed to be stable over billions of years, slowly cooling and evolving but remaining fundamentally intact. Yet around certain stars, we've discovered worlds literally evaporating before our eyes. Planets hemorrhaging millions of kilograms of atmospheric gas every second, surrounded by comet-like tails of escaping material streaming away into space. These evaporating planets shouldn't survive long in astronomical terms. The rate of mass loss is so extreme that calculations suggest they should completely disappear within millions to hundreds of millions of years. Yet here they are, caught in the act of destruction, offering us a real-time view of planetary death that challenges our assumptions about planetary longevity and atmospheric evolution. The first hints of atmospheric evaporation came from observations of HD 209458b, a hot Jupiter discovered in 1999. Early spectroscopic studies detected hydrogen escaping from the planet at velocities exceeding the escape velocity, clear evidence of an evaporating atmosphere. Later observations with the Hubble Space Telescope revealed the planet is surrounded by an enormous hydrogen cloud extending more than 200,000 kilometers from the planet's surface, roughly half the distance to the Moon. The cloud contains not just hydrogen but also heavier elements like oxygen and carbon, indicating that the escaping flow is powerful enough to drag heavier atoms along with the lighter hydrogen. The mechanism driving this escape is called hydrodynamic blow-off. The planet's upper atmosphere is heated to extreme temperatures over 10,000 Kelvin by intense ultraviolet and X-ray radiation from the nearby star. At these temperatures, the atmosphere's scale height, the vertical distance over which atmospheric pressure decreases, becomes comparable to the planet's radius. Gas at the top of this extended atmosphere reaches velocities exceeding escape velocity and streams away into space like water from a leaky faucet. The process is self-sustaining. As gas escapes, deeper atmospheric layers are exposed to stellar radiation, heat up, and continue the outflow. For HD 209458b, mass loss rates are estimated at about 10, 10 kilograms per second, roughly 100,000 tons per second. At this rate, the planet loses a significant fraction of its atmosphere over its lifetime, but because it's a massive gas giant, it can afford these losses without completely evaporating. But smaller planets face a different fate. If a Neptune-mass planet experienced similar mass loss rates, it would lose its entire hydrogen-helium envelope in just a few 100 million years, leaving behind only its rocky core, transforming from a gas planet into a super-Earth through atmospheric stripping. GJ 436b provided the first dramatic evidence of this transformation in progress. This Neptune-sized planet orbits a red dwarf star every 2.6 days at a distance of just 0.03 astronomical units. Observations revealed an enormous tail of hydrogen gas trailing behind the planet, extending more than 15 million kilometers, about 50 times the planet's diameter. The tail forms because stellar radiation pressure pushes the escaping hydrogen away from the star, creating a comet-like appearance. The planet is losing hydrogen at about 9 kilograms per second, 100,000 tons per second, a rate that would strip away a significant portion of its atmosphere over a few billion years. The discovery of evaporating rocky planets provided an even more extreme example. K2-22b, also known as KIC-11-442793, is a rocky planet about the size of Mercury, orbiting a sun-like star every 15 hours at a distance of 0.006 astronomical units. Observations revealed that the planet's transits vary in depth and duration from one orbit to the next, evidence of a dynamic, changing cloud of debris surrounding the planet. Detailed analysis showed that the planet is losing rocky material dust grains composed of silicon, iron, and other refractory elements through a process similar to atmospheric evaporation but affecting the solid surface rather than just gas. The concept of photoevaporation, atmospheric loss driven by stellar radiation, has become central to understanding the architecture of exoplanetary systems. It explains the radius valley, or Fulton Gap, observed in Kepler data, a deficit of planets with radii between 1.5 and 2 Earth radii. Planets above this size tend to retain thick hydrogen-helium atmospheres and remain as mini-Neptunes. Planets below this size have lost their primordial atmospheres entirely and appear as bare, rocky super-Earths. The valley represents the transition between these two outcomes, determined by the balance between a planet's gravity, which retains atmosphere, and the stellar radiation it receives, which drives atmospheric escape. Time-dependent models of photoevaporation predict that planets just above the radius valley will continue to shrink as they lose atmosphere, eventually crossing into the valley and settling as bare rocky cores. This means the exoplanet population we observe today is a snapshot of an ongoing process. Systems are continuously evolving as atmospheres evaporate, transforming Neptune-sized worlds into super-Earths. In a billion years, today's mini-Neptunes might become tomorrow's super-Earths, and the distribution of planet sizes will shift as atmospheric stripping reshapes planetary populations. Interestingly, the evaporation process is not uniform across all planets. Red dwarf stars, despite being cooler and less luminous than the Sun, can be even more effective at stripping atmospheres because they emit a larger fraction of their energy in the ultraviolet and X-ray wavelengths that drive photoevaporation. Planets around young, active red dwarfs experience far more intense high-energy radiation than planets around Sun-like stars, accelerating atmospheric loss. This raises questions about the long-term habitability of planets around red dwarfs. Can they retain atmospheres over billions of years, or will they be stripped bare? Observations with the James Webb Space Telescope are beginning to answer these questions by detecting atmospheric compositions of small, warm planets. Early results show a diverse range of outcomes. Some planets retain thick atmospheres despite strong stellar radiation, while others show little to no atmospheric signature, consistent with complete atmospheric loss. The presence of heavy molecules like water, carbon dioxide, or sulfur dioxide in these atmospheres provides clues about atmospheric retention mechanisms. Heavy molecules are harder to escape than hydrogen because of their greater mass, so detecting them suggests the planet either never had a hydrogen-dominated atmosphere or lost it early in its history. The long-term evolution of evaporating planets depends critically on interior structure. Planets with large rocky cores can survive atmospheric loss, becoming dense, compact super-Earths. Planets with small cores might lose so much mass that they completely disintegrate, leaving only a debris cloud or perhaps a small rocky remnant. This catastrophic disruption might explain the existence of some ultra-short period planets. They could be the surviving cores of larger planets that evaporated away, their current close orbits the result of tidal orbital decay after atmospheric loss reduced their mass. Massive gas giants far from their stars. Jupiter orbits the Sun at 5.2 astronomical units, taking nearly 12 years to complete one orbit. This location makes sense. Gas giants form beyond the ice line, where temperatures are cold enough for water to freeze, providing the solid foundation needed to accumulate massive gaseous envelopes. Theory predicts that gas giants at much greater distances, tens or hundreds of astronomical units, shouldn't exist. At those distances, the protoplanetary disk is too diffuse and cold. Orbital velocities are too slow, and the timescale for planet formation exceeds the lifetime of the gas disk. Yet we've discovered massive gas giants orbiting hundreds, even thousands of astronomical units from their stars. These distant giants defy formation models, existing in regions where planets should never grow massive enough to capture significant atmospheres. HR 8799 is the poster child for this problem. This young star, about 30 million years old and 40% more massive than the Sun, hosts 4 directly imaged giant planets. The planets orbit at 15, 25, 40 and 70 astronomical units, distances comparable to Uranus, Neptune and the outer regions of our solar system. But these aren't small icy worlds like Uranus and Neptune. They're massive gas giants, with estimated masses between 5 and 10 times Jupiter's mass. All 4 planets are still glowing from the heat of their formation, radiating infrared light that makes them detectable despite being at vast distances from their star. One proposed solution involves gravitational instability. In this scenario, rather than forming through core accretion, the gradual build-up of a solid core followed by gas capture, the planet forms directly from the collapse of a dense clump in the gas disk. If the disk is massive enough and cold enough, it can fragment under its own gravity, creating bound clumps that contract into planet mass objects. This process can occur rapidly, within thousands of years, bypassing the slow core accretion process. Numerical simulations show that gravitational instability can form massive planets at large orbital distances, but it requires specific disk conditions: high mass, low temperature, and rapid cooling. The evidence for gravitational instability versus core accretion is mixed. The HR 8799 planets have high luminosities for their masses, suggesting they're still contracting and cooling from their formation. This is consistent with gravitational instability, which predicts hot, luminous young planets because the collapse releases enormous gravitational potential energy. However, detailed atmospheric modelling shows these planets have relatively high metallicities, more heavy elements than expected for simple gravitational collapse of gas. This argues for core accretion, which naturally produces metal-rich planets because the solid core contributes significant heavy elements. Another enigmatic system is Beta Pictoris, a young star about 20 million years old located 63 light-years from Earth. It hosts at least 2 confirmed planets. Beta Pictoris b orbits at roughly 9 astronomical units, while Beta Pictoris c orbits at about 2.7 astronomical units. Beta Pictoris b has a mass around 13 times Jupiter's mass and shows evidence of ongoing accretion. It's still pulling in material from the surrounding disk. The planet orbits within a prominent debris disk visible in infrared images, a disk of dust and planetesimals left over from planet formation. The disk shows asymmetries and warps that are likely caused by gravitational interactions with the planets, providing direct evidence of ongoing dynamical evolution. One of the most distant, directly imaged planets is GU Piscium b, orbiting at an astonishing 2,000 astronomical units from its host star, about 50 times Neptune's distance from the Sunday. At this separation, the orbital period exceeds 80,000 years. The planet's mass is roughly 11 times Jupiter's mass. Its existence at such an enormous distance challenges every formation mechanism. Core accretion is essentially impossible. There's not enough material, and orbital timescales are absurdly long. Even gravitational instability struggles at these distances because disk masses would need to be enormous, and interactions with other stars in the birth cluster would likely disrupt such extended disks. This has led to alternative hypotheses. Perhaps GU Piscium b didn't form in a disk at all, but instead formed like a binary companion through the same fragmentation process that creates binary star systems. In this scenario, the planet is really a very low-mass brown dwarf or star that formed alongside its host through cloud fragmentation. The dividing line between a planet and a brown dwarf becomes ambiguous, defined more by formation mechanism than by mass alone. If GU Piscium b formed through stellar-like processes, should we even call it a planet? Statistical studies of directly imaged planets show they're rare. Only about 1% of Sun-like stars host detectable giant planets beyond 30 astronomical units. This rarity contrasts sharply with closer-in planets, which are common. The scarcity of distant giants supports the idea that forming massive planets at large distances requires special conditions, either unusually massive and extended protoplanetary disks or gravitational instability, both of which are uncommon. The long-term dynamics of widely separated giant planets are also peculiar. At hundreds of astronomical units, planets are weakly bound to their stars. Passing stars, encounters with molecular clouds, or even the tidal forces from the galaxy can perturb their orbits, potentially ejecting them from their systems entirely. Wide-orbit planets might represent a transitional population. Some will survive to old age, while others will be stripped away, becoming rogue planets drifting through interstellar space. Another puzzle involves the architectures of systems with distant giants. HR 8799 has 4 massive planets between 15 and 70 astronomical units. How did all 4 form and survive? Gravitational interactions among such massive planets should lead to instabilities, ejecting one or more planets or driving them into the star. Computer simulations show that the HR 8799 system is near the edge of stability. The planets must be in or near mean motion resonances with each other, configurations where their orbital periods form simple integer ratios that stabilize the system through constructive gravitational interactions. Observations haven't yet confirmed these resonances, but they remain the best explanation for how the system has survived for 30 million years without destroying itself. Planets around pulsars. Pulsars are among the most extreme objects in the universe, the rapidly spinning remnants of massive stars that exploded as supernovae. These neutron stars pack more than the Sun's mass into a sphere just 20 kilometers across, creating surface gravities 100 billion times stronger than Earth's and magnetic fields, 1 trillion times more intense than anything we can produce in laboratories. They spin at incredible rates, sometimes hundreds of times per second, beaming radiation from their magnetic poles like cosmic lighthouses. The environment around a pulsar is hell-intense radiation, powerful magnetic fields, and the shattered debris from the supernova that created them. Planets should not exist in such places. Yet they do, and their presence has forced us to reconsider not just how planets form, but how resilient they can be. The first exoplanets ever discovered orbit a pulsar. In 1992, astronomers Alexander Wolszczan and Dale Frail detected 3 planets around PSRB 1000, 257 plus 12, a pulsar located about 2,300 light-years from Earth. The discovery was accidental. Wolszczan was studying the pulsar's timing, measuring the precise intervals between radio pulses. Pulsars are extraordinary clocks. Their rotation periods are stable to better than 1 part in a billion. But PSRB 1257 plus 12's pulses showed tiny periodic variations, sometimes arriving slightly early, sometimes slightly late. These timing variations followed patterns consistent with the gravitational pull of orbiting planets tugging the pulsar back and forth. The planets, designated PSRB 1257 plus 12b, C and D, have masses of 0.02, 4.3, and 3.9 Earth masses respectively. The 2 larger planets orbit at 0.36 and 0.46 astronomical units, with periods of 66.5 and 98.2 days, positions that would place them roughly where Mercury orbits in our solar system. The smallest planet orbits much closer, at just 0.19 astronomical units. All 3 planets have nearly circular orbits and appear to be rocky, based on their masses and the absence of detectable gas signatures. The discovery was revolutionary, but also baffling. Supernovae, the explosions that create neutron stars, release more energy in a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The blast wave travels outward at 10,000 to 30,000 kilometers per second, vaporizing anything within several astronomical units. Any planets orbiting the progenitor star should have been destroyed utterly, either blown away by the explosion or consumed as the star collapsed. The existence of planets around PSR B 1257 plus 12 meant they must have formed after the supernova, from debris left behind by the explosion. Current models propose that pulsar planets form from a fallback disk. After a supernova, some of the ejected material doesn't escape the neutron star's gravity. Instead, it falls back, forming a disk of gas, dust, and heavier elements around the pulsar. This disk is similar to a protoplanetary disk around a young star, but with critical differences. It's metal-rich, containing iron, silicon, and other heavy elements synthesized in the supernova explosion. It's also extremely hot and bathed in intense radiation from the pulsar. Despite these harsh conditions, planets can form through the same processes of dust grain coagulation and gravitational accretion that occur in normal protoplanetary disks, just on a much faster timescale, perhaps within a few thousand years while the disk is still hot and active. PSR B 1257 plus 12 isn't alone. A few other pulsars show evidence of orbiting planets or planetary mass objects. PSR B 162026, located in the globular cluster M4, hosts a planet about 2.5 times Jupiter's mass, orbiting at 23 astronomical units. This planet is remarkable not just because it orbits a pulsar, but because the pulsar itself orbits a white dwarf star, making the planet part of a triple system. The planet's age is extraordinary, roughly 12.7 billion years, making it one of the oldest known planets in the galaxy, formed when the universe was less than 1 billion years old. The environment on a pulsar planet would be utterly alien. The intense magnetic field would create powerful auroras if the planet had an atmosphere, though maintaining an atmosphere seems unlikely given the pulsar's radiation. The planet would be bathed in X-rays and gamma rays from the pulsar's magnetic poles, receiving radiation doses thousands of times higher than Earth receives from the Sunday. If the planet's orbit happened to pass through the pulsar's beam, the radiation intensity would fluctuate wildly with the pulsar's rotation period, creating a strobe light effect cycling hundreds of times per second. Despite these conditions, pulsar planets are remarkably stable. Measurements of PSR B 1257 plus 12's planets spanning nearly 3 decades show that their orbits haven't changed detectably. No orbital decay, no eccentricity variations, no resonance shifts. This stability is surprising given the complex gravitational environment. The pulsar's intense magnetic field and rotation create a quadrupole moment, a deviation from perfect spherical symmetry that can perturb orbits. Yet the planets remain in lockstep, their orbits precisely circular and stable. The formation of planets around pulsars raises intriguing questions about planet formation's robustness. If planets can form in the aftermath of a supernova, one of the most violent events in the universe, then planet formation might be far more common and resilient than we thought. Almost any rotating disk of material, given enough time and the right conditions, might produce planets. This universality could explain why exoplanets are so diverse and why we find them in environments we never expected, from ultra-close orbits to extreme distances, from sun-like stars to stellar corpses. Searches for additional pulsar planets continue, using increasingly precise timing measurements. Modern pulsar timing arrays can detect variations as small as a few nanoseconds, precise enough to find Earth-mass planets, or even large moons if they exist. So far, most pulsars show no evidence of planets, suggesting that either the formation conditions aren't common, or that many pulsar planets have been destroyed or ejected through interactions with other objects or radiation pressure. One final mystery surrounds pulsar planets: their long-term fate. Pulsars gradually slow down as they lose rotational energy to their magnetic fields and radiation. Over hundreds of millions of years, they spin down until their emission becomes too weak to detect. They die, becoming inert neutron stars. What happens to their planets? Do they remain in orbit around the now silent stellar corpse, frozen and dark, or do gravitational perturbations eventually disperse them into interstellar space? Without the pulsar's beam to illuminate their presence, these planets would become effectively invisible, impossible to detect with current technology, leaving their ultimate fate uncertain. The superpuff planets. Density is one of the most fundamental properties of a planet. Earth has a density of 5.5 grams per cubic centimetre, mostly from its iron core and rocky mantle. Jupiter, despite being a gas giant, has a density of 1.3 grams per cubic centimetre due to the compression of hydrogen under its own enormous gravity. Saturn, the least dense planet in our solar system, comes in at 0.7 grams per cubic centimetre, low enough that it would float in water, if you could find an ocean big enough. These numbers make sense based on our understanding of how gravity compresses matter. Then astronomers discovered planets with densities less than 0.1 grams per cubic centimetre less dense than styrofoam, approaching the density of cotton candy. These superpuff planets shouldn't exist according to our models of planetary structure. Their masses are too low to hold such enormous atmospheres, and no known composition can explain their extreme fluffiness. The first superpuff planet, Kepler 51b, was discovered in the Kepler data in 2012, but its true nature wasn't recognized until 2014, when precise mass measurements became available. The planet has a radius about 9 times Earth's radius, similar to Saturn, but a mass of only about 6 Earth masses. This gives it a density of roughly 0.03 grams per cubic centimetre, about 1/200th Earth's density. 2 other planets in the Kepler 51 system, designated C and D, show similarly low densities. All 3 planets orbit their star at distances between 0.25 and 0.5 astronomical units, with orbital periods ranging from 45 to 130 days. The extreme puffiness of these planets defies explanation. To achieve such low densities, the planets must consist almost entirely of hydrogen and helium, with only tiny rocky or icy cores. But planets with such small cores shouldn't be able to capture and retain such massive gaseous envelopes, especially at the relatively warm temperatures where Kepler 51's planets orbit. The equilibrium temperatures of these planets range from about 500 to 700 Kelvin, warm enough that hydrogen molecules move at high velocities, making atmospheric escape efficient. According to standard models, planets this small should lose their hydrogen atmospheres within tens of millions of years. Yet Kepler 51 is several hundred million years old, and its planets still possess enormous atmospheres. One proposed explanation involves unusually low atmospheric opacity. Opacity determines how easily radiation can escape from a planet's interior. High opacity traps heat, puffing up the atmosphere. Normal planetary atmospheres contain molecules like water, methane, and various hydrocarbons that absorb infrared radiation, creating opacity. If superpuff atmospheres somehow lack these molecules, if they consist of almost pure hydrogen and helium, they would have much lower opacity, allowing heat to escape easily. But this creates a paradox. Lower opacity leads to faster cooling, which should cause the atmosphere to contract, increasing density. Yet superpuffs remain inflated. Another idea invokes dust. If the upper atmospheres of superpuffs contain high-altitude dust clouds composed of tiny grains of minerals or photochemical hazes, these could absorb starlight and heat the upper atmosphere. This heating would create a temperature inversion, where temperature increases with altitude instead of decreasing, which could inflate the atmosphere to extreme sizes. Evidence from transmission spectroscopy supports this hypothesis. Observations of Kepler 51 planets show featureless spectra. No molecular absorption features are detectable. This flat spectrum is consistent with thick, high-altitude haze layers that block light before it can penetrate to deeper atmospheric layers where molecules would leave their spectral signatures. HIP 41378f provides another example of extreme puffiness. This planet has about 12 Earth radii and 9 Earth masses, giving it a density around 0.09 grams per cubic centimetre. It orbits at 1 astronomical unit from a Sun-like star, roughly Earth's orbital distance, where temperatures should be moderate, around 300 Kelvin. At this distance and temperature, holding on to such a bloated atmosphere seems even more impossible. The planet's size is so large that it transits its star for over 16 hours each orbit, creating one of the longest duration transits ever observed. The age of superpuff planets provides clues about their nature. Kepler 5.1 is about 500 million years old young, but old enough that rapid atmospheric escape should have significantly altered the planet's structures. HIP 41378 is roughly 1 billion years old. If these atmospheres are genuinely primordial left over from formation, they must be extraordinarily stable against mass loss. Alternatively, they could be actively replenished by outgassing from the interior, though the required gas production rates seem unrealistically high. Tidal heating offers another possibility. If superpuff planets have eccentric orbits or are locked in orbital resonances with other planets, tidal forces from the star could flex their interiors, generating heat. This internal heating could inflate the atmosphere from below, maintaining the puffiness over long timescales. However, most observed superpuffs have nearly circular orbits and show no evidence of strong tidal interactions, making this explanation less likely. The long-term evolution of superpuff planets remains uncertain. Are they young objects that will gradually contract as they age and lose atmosphere, or do they represent a stable configuration that can persist for billions of years? Observations of superpuffs around older stars could answer this question, but so far, nearly all known superpuffs orbit relatively young stars, consistent with the idea that they're a transient phase in planetary evolution. Some researchers have proposed that superpuffs are in the process of rapid mass loss, that we're observing them during a brief period when their atmospheres are evaporating. The planets might currently be shedding gas at enormous rates, with outflow velocities high enough to inflate their apparent size. In this scenario, superpuffs would shrink over time, eventually becoming dense super-Earths after losing most of their hydrogen. This would explain why they're so rare we're catching them during a brief transitional phase lasting only a few 100 million years. The rarity of superpuffs supports this transient interpretation. Despite Kepler surveying hundreds of thousands of stars, only a handful of superpuff planets have been identified. Either they form rarely, or they don't last long. If they're transient, then for every superpuff we observe now, many more might have existed in the past and have since evolved into denser configurations. Attempts to directly observe superpuff atmospheres with the James Webb Space Telescope are underway. JWST's superior sensitivity and wavelength coverage should be able to penetrate any hazes and detect molecular absorption features that reveal atmospheric composition. If superpuffs contain unusual molecules or show evidence of extreme chemistry, it would support the idea that their structures are fundamentally different from normal gas planets. If they show standard hydrogen-helium atmospheres with normal opacity sources, it would deepen the mystery of how they maintain such extreme puffiness. Planets in extreme eccentric orbits. Planets in our solar system follow nearly circular orbits. Earth's orbital eccentricity is just 0.017, meaning its distance from the Sun varies by only 3% over the course of a year. Even Mercury, with the most eccentric orbit of any solar system planet, has an eccentricity of only 0.206. These low eccentricities result from the damping effects of the protoplanetary disk during formation and from long-term gravitational interactions that circularize orbits over millions of years. We expected exoplanetary systems to follow similar patterns. Instead, we discovered planets on wildly eccentric orbits, swinging from scorching close approaches to frigid distant excursions, experiencing temperature swings of hundreds of degrees over the course of single orbits. These extreme eccentricities shouldn't persist. Gravitational interactions and tidal forces should have circularized the orbits long ago. Yet dozens of highly eccentric exoplanets exist, their orbital paths resembling stretched ellipses more than circles. HD 80606b holds the record for the most extreme eccentric orbit of any well-characterized exoplanet, with an eccentricity of 0.93. This gas giant, about 4 times Jupiter's mass, swings from 0.03 to 0.88 astronomical units over its 111-day orbit. At closest approach periastron, the planet passes just 3 million kilometers from its star's surface, well within the orbit of Mercury. The star's radiation heats the planet's atmosphere by more than 700 Kelvin in just 6 hours, triggering massive atmospheric changes. Supersonic winds race around the planet at over 3,000 kilometers per second, redistributing heat from the irradiated day side to the cooler night side. Then the planet swings back out to nearly the distance of Venus. spending most of its orbit in relative cold before plunging inward again. Observations of HD 80606b during periastron passage using the Spitzer Space Telescope captured the planet's thermal response in real time. As the planet approached its star, its infrared brightness spiked dramatically, the dayside temperature soaring from about 800 Kelvin to 1500 Kelvin in less than 6 hours. The planet's atmosphere couldn't equilibrate fast enough, creating enormous pressure gradients that drove violent storm systems and planetary-scale shock waves. After passing periastron, the planet cooled gradually as it receded, its brightness dimming over several days as heat radiated back into space. The formation of such extreme eccentricities requires violent dynamical events. Planets don't form on eccentric orbits. The protoplanetary disk's gas drag circularizes orbits within millions of years. High eccentricities must be excited after the disk dissipates, through gravitational interactions among planets or with external perturbers. The most common mechanism is planet-planet scattering. In systems where multiple giant planets form with certain orbital configurations, gravitational interactions can become chaotic. One planet's orbit might grow more eccentric while another is ejected entirely from the system or crashes into the star. The surviving planet ends up on a highly eccentric orbit as a result of the violent encounter. HD 80606's extreme eccentricity likely resulted from the Kozai leadoff mechanism, a gravitational effect that occurs in hierarchical triple systems. HD 80606 is part of a binary star system. Its host star has a distant stellar companion orbiting several hundred astronomical units away. The companion's gravity can induce oscillations in the planet's orbit, periodically exchanging orbital eccentricity and inclination. Over millions of years, these oscillations can pump up the planet's eccentricity to extreme values. Tidal forces from the host star then gradually circularize the orbit at periastron, but the Kozai cycles can maintain high eccentricity for billions of years if the balance is right. The long-term stability of eccentric orbits depends on tidal circularization timescales. When a planet on an eccentric orbit passes close to its star, tidal bulges raised on the planet lag behind the planet's rotation due to internal friction. This tidal lag transfers energy from the planet's orbit to the star's rotation, gradually circularizing the orbit and shrinking the semi-major axis. For close-in planets, this process can circularize orbits in less than 1 billion years. But for planets with periastron distances greater than about 0.1 astronomical units, tidal circularization takes tens of billions of years longer than the current age of the universe. This explains why some eccentric planets persist. They simply haven't had enough time to circularize yet. WASP 1-2b represents a case where tidal circularization is actively reshaping the system. This planet orbits every 1.1 days at just 0.023 astronomical units, so close that the star's gravity is distorting the planet into an ellipsoid shape. Tidal dissipation is causing the orbit to decay at a measurable rate. The planet's orbital period is decreasing by about 29 milliseconds per year. At this rate, the planet will spiral into its star in approximately 3 million years, a blink of an eye in astronomical terms. Observations spanning a decade have confirmed this orbital decay, making WASP 1-2b one of the first planets where we've directly measured the death spiral predicted by tidal theory. Another extreme case is HD 20782b, a gas giant with eccentricity 0.96, even higher than HD 80606b. This planet swings from 0.06 to 2.5 astronomical units over a 597-day orbit. At a pastron, the planet orbits farther from its star than Mars orbits the Sun. At periastron, it skims closer than Mercury. The temperature variation over one orbit exceeds 1000 Kelvin. Such extreme ellipticity raises questions about atmospheric stability. Can the planet retain an atmosphere under such conditions, or does the periastron passage strip away atmospheric gas that then doesn't fully reaccrete during the outer portions of the orbit? Statistical studies of exoplanet eccentricities reveal interesting patterns. Hot Jupiter's gas giants orbiting very close to their stars almost always have circular orbits, consistent with rapid tidal circularization. Gas giants orbiting beyond about 0.1 astronomical units show a wide range of eccentricities, from nearly circular to highly elliptical, suggesting diverse dynamical histories. Small planets, super-Earths and sub-Neptunes tend to have lower eccentricities than gas giants, possibly because systems with small planets are more dynamically stable, or because small planets can't survive the violent scattering events that produce eccentric orbits. Planets orbiting in reverse. When planets form from a protoplanetary disk, they inherit the disk's rotation. The disk spins in the same direction as the star, and planets form within it, naturally adopting orbits that circle the star in the same direction, what astronomers call prograde rotation. This is how our solar system works. All 8 planets orbit the Sun in the same direction, following the conservation of angular momentum from the original solar nebula. It's a fundamental principle written into the physics of rotating systems. Then we discovered planets orbiting backward. These retrograde planets move in the opposite direction to their star's rotation, swimming upstream against the cosmic current that created them. The first confirmed example was WASP 17b, discovered in 2009. This bloated hot Jupiter orbits its star every 3.7 days, but spectroscopic measurements of the Rossiter-McLaughlin effect, the distortion of stellar spectral lines during planetary transits, revealed something shocking. The planet's orbit is tilted 148 degrees relative to the star's equator. That's not just tilted, it's completely backward. The planet circles its star in the opposite direction to the star's rotation. The discovery was deeply unsettling. Planets can't form on retrograde orbits. The gas and dust in a protoplanetary disk all move together, in the same direction, like water swirling down a drain. A planet forming within that disk has no choice but to follow the flow. For WASP 17b to orbit backward means something violent happened after formation, something powerful enough to completely flip the planet's orbital direction. Planet-planet scattering provides the most likely explanation. If WASP 17b formed as part of a multi-planet system, gravitational interactions with another massive planet could have altered its orbit dramatically. During close encounters, one planet can gain energy and orbital inclination, while the other loses it. If the interaction is violent enough, a planet can be kicked onto a highly inclined or even retrograde orbit. The other planet involved in the scattering might have been ejected from the system entirely, or it might have crashed into the star, leaving WASP 17b as the sole survivor of a chaotic gravitational battle. Following WASP 17b's discovery, surveys found dozens more retrograde or highly inclined hot Jupiters, HAT-P, 7b orbits at an angle of 182 degrees, nearly perfectly retrograde. WASP 79b shows an inclination of 106 degrees, while Kepler 419c orbits at 162 degrees. These aren't rare flukes. Statistical studies suggest that roughly 25% of hot Jupiters around hot stars have orbits that are significantly misaligned with their star's rotation, with a substantial fraction on retrograde orbits. The prevalence of retrograde planets reveals something profound about planetary system evolution. Our solar system, with its orderly, coplanar, prograde orbits, isn't typical, it's unusually calm and stable. Most planetary systems apparently experience violent dynamical upheavals during their early history. Multi-planet interactions, scattering events, and close encounters scrambled orbital configurations, leaving behind survivors on tilted, eccentric, or retrograde paths. The planets we see today are the lucky ones that didn't get ejected or consumed. Another mechanism that can produce retrograde orbits involves the Kozai-Lidov effect in binary star systems. If a planet orbits one star while a distant companion star orbits farther out, the companion's gravity can induce oscillations in the planet's orbit, periodically flipping it between prograde and retrograde configurations over millions of years. During these oscillations, the planet's eccentricity and inclination exchange. As inclination increases, eccentricity increases, bringing the planet closer to the star at periastron. Tidal forces then circularize the orbit, locking the planet into a close, potentially retrograde configuration. The existence of retrograde planets has implications for tidal interactions and spin-orbit coupling. When a planet orbits in the same direction as its star rotates, tidal forces gradually synchronize the system. The planet's orbit shrinks while the star's rotation slows, conserving angular momentum. But when a planet orbits retrograde, the tidal interaction works differently. The planet's orbital angular momentum and the star's rotational angular momentum point in opposite directions. As tidal forces act, they can't easily synchronize. Instead, the star's rotation might slow dramatically, or the planet's orbit might decay rapidly, leading to faster in-spiral and eventual consumption. WASP 12b, mentioned earlier for its orbital decay, might owe its short remaining lifetime partly to misalignment effects. While not fully retrograde, its orbit is significantly tilted relative to the star's equator. This misalignment reduces the efficiency of tidal angular momentum transfer, accelerating orbital decay. The planet is spiraling into its star measurably faster than a perfectly aligned planet would, demonstrating how orbital architecture affects long-term stability. Retrograde planets also challenge planet migration theories. The standard Type II migration scenario, where planets spiral inward through interactions with the gas disk, naturally preserves prograde motion. The planet moves inward, but continues orbiting in the disk's rotation direction. To produce retrograde orbits requires additional mechanisms beyond simple disk migration. Either violent dynamical scattering occurred after the disk dispersed, or the planets underwent disk migration followed by subsequent gravitational perturbations that flipped their orbits. Both scenarios imply complex, multi-stage evolutionary histories. Observations with high-precision spectrographs have revealed even stranger configurations. Some planets orbit nearly perpendicular to their star's equator, polar orbits with inclinations around 90 degrees. These planets aren't quite retrograde but aren't prograde either. They circle their stars from pole to pole rather than around the equator. Kepler 63b, for example, has an orbital inclination of about 104 degrees, placing it in a near-polar orbit. Such configurations are even harder to explain than simple retrograde motion, requiring multiple scattering events or complex Kozai cycles involving multiple companions. The study of misaligned and retrograde planets has expanded beyond hot Jupiters to include smaller planets and longer-period worlds. Some super-Earths show evidence of orbital misalignment, though measuring inclinations for smaller planets is more challenging. If misalignment proves common even among rocky planets, it would suggest that dynamical chaos is a universal feature of planetary system evolution, affecting not just gas giants but all planet types. One final puzzle involves the relationship between stellar properties and orbital alignment. Hot Jupiters around cool stars, spectral types F, G, K, M, tend to have well-aligned orbits, while those around hot stars, spectral types A, B, show much higher rates of misalignment and retrograde motion. This correlation suggests that the star's properties, perhaps its magnetic field strength, tidal dissipation efficiency, or rotational history, play a role in determining whether orbits remain aligned or become scrambled. Hot stars have thin convective zones and weaker magnetic fields, which might affect how tidal forces realign orbits over time. Water worlds drowning in the ocean. Earth is often called the blue planet because oceans cover about 71% of its surface, but these oceans are shallow, averaging just 3.7 kilometers deep, and contain only about 0.02% of Earth's total mass. The vast majority of our planet is rock and metal. We've long assumed that other habitable planets would be similar rocky worlds with surface oceans, perhaps slightly larger or smaller than Earth's seas, but fundamentally similar in architecture. Then detailed modelling of exoplanet compositions revealed a category we never anticipated: true water worlds. Planets where water comprises 30, 40, even 50% of the total mass. These aren't planets with oceans, they're planets made of ocean, with global seas hundreds of kilometers deep, possibly lacking any solid surface at all. The first hints came from mass and radius measurements of certain super-Earths and sub-Neptunes. When you measure a planet's mass and radius, you can calculate its density, which constrains its composition. High density indicates rock and iron. Low density suggests gas. But some planets fell into an intermediate range, too dense to be gas giants, too light to be pure rock. The best fit to their densities required substantial amounts of water, implying that these planets are neither rocky nor gaseous but something in between, icy or water-rich worlds. But the story gets stranger. In a true water world, the ocean's weight creates enormous pressures at depth. At depths of 100 kilometers, pressures exceed 10,000 atmospheres, enough to form Ice 7, a dense crystalline solid. At 200 kilometers depth, pressures reach 100,000 atmospheres, creating even more exotic ice phases. This means a water world's structure would be fundamentally different from Earth's. A relatively thin layer of liquid water at the surface, transitioning to a thick mantle of high-pressure ice below, and perhaps a rocky or metallic core at the centre if any rocky material exists at all. This structure has profound implications for habitability. On Earth, the interaction between water and rock is crucial for maintaining a stable climate. Chemical weathering of silicate rocks consumes atmospheric carbon dioxide, which is then transported to the oceans and deposited as carbonate minerals on the seafloor. Plate tectonics recycles these carbonates back into the mantle, where they're heated and released as volcanic carbon dioxide, completing the carbon cycle. This feedback mechanism has stabilized Earth's climate for billions of years, preventing runaway greenhouse or icehouse conditions. On a water world with an ocean hundreds of kilometers deep, this rock-water interaction might not occur. If a thick layer of high-pressure ice separates the liquid ocean from the rocky interior, there's no mechanism for chemical weathering, no carbonate-silicate cycle, no plate tectonics. Without these stabilizing feedbacks, the planet's climate could be far more volatile. Atmospheric carbon dioxide levels might drift unpredictably, causing wild temperature swings that make long-term habitability challenging. Alternatively, some water worlds might lack rocky cores entirely. If a planet formed far from its star, beyond the ice line where water freezes, it could accrete mostly ice and only small amounts of rock. Such a planet would be essentially a giant snowball, a sphere of water and ice with perhaps some silicate dust mixed in, but no substantial rocky core. These ocean planets, or ice giants without the gas, would have entirely liquid or ice interiors all the way to the center, creating internal structures unlike anything in our solar system. The formation of water worlds requires special conditions. In the inner solar system, where Earth formed, temperatures were too high for water ice to condense. Only rocky and metallic materials could survive, producing rocky planets. Water reached Earth through asteroid and comet impacts long after formation, delivering perhaps 5 to 10% of Earth's water from the outer solar system. But in planetary systems where the ice line, the boundary beyond which water freezes, lies closer to the star, planets could accrete water-rich material directly during formation. The prospect of life on water worlds raises intriguing questions. On Earth, life began in the oceans, but it eventually colonized land, where evolutionary innovations like photosynthesis, complex multicellular structures, and eventually intelligence developed. If water worlds lack land entirely, could complex life still evolve? Would it remain aquatic forever? Could intelligence develop in a purely oceanic environment? Some researchers argue that landless water worlds might actually be hostile to life. Without exposed rock surfaces, there's no weathering, no nutrient cycling from land to sea, no tidal pools where prebiotic chemistry might concentrate organic molecules. The deep oceans would be dark and cold, far from any energy source. Life might struggle to gain a foothold without the interfaces and chemical gradients that land-sea boundaries provide on Earth. Others counter that subsurface hydrothermal systems could provide energy and nutrients. If water worlds have rocky cores beneath their ice mantles, tidal heating or residual radioactive decay could drive hydrothermal circulation, creating seafloor vents similar to those on Earth that host extremophile ecosystems. These vent communities don't depend on sunlight. They derive energy from chemical reactions between seawater and volcanic minerals. Similar ecosystems could exist on water worlds, thriving in the dark depths where liquid water meets rocky core. The detection and characterization of water worlds remains challenging. Measuring mass and radius can identify candidates, but confirming their water-rich nature requires atmospheric spectroscopy. The James Webb Space Telescope is beginning to probe super-Earth atmospheres, searching for spectroscopic signatures of water vapor. If a planet shows abundant water vapor in its atmosphere and has a density consistent with a large water fraction, it strengthens the case for a water world interpretation. However, distinguishing between different scenarios, a rocky planet with a thick, steamy atmosphere versus a true water world with global oceans requires detailed modeling. A planet with a hydrogen-rich atmosphere can also have a low density, mimicking a water world. Transmission spectroscopy during transits can reveal atmospheric composition, but inferring interior structure from atmospheric observations is model-dependent and uncertain. The long-term evolution of water worlds depends on atmospheric loss. Planets with thick water vapor atmospheres orbiting close to their stars can lose water through photodissociation. Ultraviolet light splits water molecules into hydrogen and oxygen. The light hydrogen escapes to space, while oxygen might remain, accumulate, or be lost more slowly. Over billions of years, a water world could gradually desiccate, losing its global ocean and transitioning to a dry, rocky planet with an oxygen-rich atmosphere. Observations of such planets might reveal the fossil remnants of ancient water worlds, oxidized surfaces, and oxygen atmospheres indicating lost oceans. Planets denser than they should be. Density reveals a planet's composition. Rocky planets like Earth have densities around 5 to 6 grams per cubic centimetre, set by the iron and silicate minerals that dominate their interiors. Gas giants like Jupiter have much lower densities, around 1.3 grams per cubic centimetre, because they're mostly hydrogen and helium, held together by gravity but not compressed to the densities of solid materials. These relationships follow predictable patterns based on how matter behaves under pressure. Then we discovered planets with densities that violate these patterns, rocky worlds far denser than they should be, packed with materials in proportions that make no sense according to standard planetary formation models. The first ultra-dense exoplanet was Corot, 3b, discovered in 2008. This planet has a mass of about 22 Jupiter masses, but a radius only slightly larger than Jupiter's, giving it a density of about 26 grams per cubic centimetre, nearly 5 times Jupiter's density and significantly higher than Earth's. For comparison, pure iron has a density of 7.9 grams per cubic centimetre at Earth's surface, though it compresses to higher densities under planetary interior pressures. To achieve Corot, 3b's extreme density requires either an iron-rich composition far exceeding anything in our solar system, or exotic interior states of matter we don't fully understand. The planet's mass places it near the boundary between planets and brown dwarfs, failed stars too small to sustain hydrogen fusion. Objects above about 13 Jupiter masses can briefly fuse deuterium in their cores, a transitional process between planetary and stellar physics. Corot, 3b's mass of 22 Jupiter masses, puts it well into brown dwarf territory based on mass alone, but its formation in a planetary system and its orbital characteristics suggest it formed like a planet rather than like a star. Whether we call it a planet or a brown dwarf becomes a semantic question, highlighting the fuzzy boundary between these categories. But Corot, 3b, isn't alone. Several other planets show densities far higher than expected for their masses. TOI, 849b, discovered in 2020, has a mass of about 40 Earth masses, but a radius only 3.4 times Earth's radius. This gives it a density around 5.5 grams per cubic centimetre, similar to Earth's density despite being 40 times more massive. For a planet this massive to be so small and dense, it must be almost entirely rock and iron, with little to no atmosphere. This composition is extraordinarily unusual. Planets with masses around 40 Earth masses should accrete significant hydrogen and helium atmospheres, becoming mini-Neptunes or even full gas giants. The gravity at 40 Earth masses is more than sufficient to capture and retain gas from the protoplanetary disk. Yet TOI 849b appears to be a bare, rocky core. The most plausible explanation is that TOI 849b is the exposed core of a former gas giant, a planet that lost its entire gaseous envelope through some catastrophic process. Several mechanisms could strip away a gas giant's atmosphere. Energetic collisions with other planets could blast away the gaseous envelope, leaving only the core. Photoevaporation from intense stellar radiation could erode the atmosphere over time. Tidal stripping from a close stellar encounter could remove gas while leaving the denser core intact. Any of these processes would leave behind an ultra-dense remnant, a planet that was once much larger but lost most of its mass, creating the anomalous density we observe. K2 229b provides another example of extreme density. This planet has a mass of about 2.6 Earth masses and a radius of only 1 Earth radii, giving it a density of roughly 8 grams per cubic centimetre, significantly higher than Earth's 5.5 grams per cubic centimetre. To achieve this density requires an iron-rich composition. Models suggest K2 229b is about 70% iron by mass, compared to Earth's 32%. This planet is essentially a giant iron ball with a thin rocky mantle. The formation of such iron-rich planets is difficult to explain. In our solar system, Mercury is the most iron-rich planet, with an iron core comprising about 70% of its mass. But Mercury's overall density is still only about 5.4 grams per cubic centimetre due to its lower mass, less compression, and rocky mantle. To create a planet as iron-rich as K2 229b requires removing much of the rocky mantle while retaining the iron core. This could occur through giant impacts during formation collisions, energetic enough to vaporize and blow away silicate rock while leaving the denser iron behind. Computer simulations of giant impacts show that under specific conditions, collisions can preferentially remove rocky material. When two protoplanets collide at high velocities, the impact generates enormous heat, vaporizing silicate rock. The vapor expands rapidly and can escape the collision site, especially if the impact velocity exceeds the mutual escape velocity of the colliding bodies. Iron, being denser and less volatile, doesn't vaporize as easily and remains gravitationally bound. The net result is a merged body with an enhanced iron fraction, exactly what K2 229b appears to be. This scenario draws parallels to Mercury's formation in our solar system. Mercury's high iron content has long been attributed to one or more giant impacts that stripped away much of its silicate mantle. If this process occurred during Mercury's formation, it could occur during exoplanet formation as well, potentially even more extremely, creating planets with iron fractions far exceeding Mercury's. Possible explanations include an unusually large core, perhaps 50 to 100 Earth masses of rock and ice beneath the hydrogen-helium envelope. Such a massive core would increase the planet's overall density and resist the atmospheric inflation that stellar heating would otherwise cause. But forming such a large core is challenging. It requires accumulating enormous amounts of solid material before the gas disk dissipates, implying very rapid formation or unusual disk conditions. This correlation between stellar metallicity and planetary density has been observed in multiple systems. Metal-rich stars tend to host denser planets, consistent with the idea that planet composition reflects the composition of the natal disk. If the disk contains more metals and fewer volatiles, planets forming from that disk will be denser. This effect is most pronounced for giant planets, where the ratio of heavy elements to hydrogen and helium varies significantly depending on formation conditions. The study of ultra-dense planets has implications for understanding planetary interiors and the diversity of formation outcomes. Standard models predict certain density ranges for given masses and compositions, but nature produces planets outside these ranges, forcing us to consider additional processes: giant impacts, atmospheric stripping, metal-rich formation environments, and extreme core masses. Each ultra-dense planet is a clue, a data point that constrains the range of possible planetary outcomes and tests the limits of formation theory. Planets with disappearing transits. One of the most powerful techniques for discovering exoplanets is the transit method. When a planet passes in front of its star from our viewpoint, it blocks a tiny fraction of the star's light, creating a brief dimming event. These transits are predictable once you know a planet's orbital period. You can calculate precisely when the next transit will occur. Astronomers rely on this predictability to schedule follow-up observations, study planetary atmospheres, and refine orbital parameters. The transits should be clockwork regular, occurring with metronomic precision every orbit. Then we discovered planets whose transits disappear. KIC 125575448b was the first planet observed to have disappearing transits. Discovered by the Kepler mission, this planet orbits its star every 15.7 hours, an ultra-short period, placing it at just 0.01 astronomical units from its host star. The planet transits every orbit, but the depth of these transits varies wildly. Sometimes the planet blocks about 1.3% of its star's light. Other times it blocks only 0.2%, and occasionally it seems to produce no detectable transit at all. This variability is unprecedented for a solid planetary body. The planet's physical size shouldn't change from orbit to orbit. The explanation involves dust. KIC 125575448b isn't just a planet, it's a disintegrating planet. The extreme stellar radiation at its close orbital distance vaporizes rocky material from the planet's surface. creating a thin atmosphere of silicate vapor. This vapor escapes the planet's weak gravity. The planet is tiny, only about half Earth's radius, and flows away into space, where it cools and condenses into tiny dust grains. These dust grains form a dynamic, comet-like tail trailing behind the planet, extending millions of kilometers along its orbit. When the planet transits, we're not just seeing the planet itself block starlight, we're seeing the planet plus its variable dust tail. If the tail is dense and extended, it blocks additional starlight, making the transit deeper. If the tail is thin or disrupted, less light is blocked, making the transit shallower or even undetectable. The variability arises because the dust production rate fluctuates with surface conditions, stellar activity, and random factors like local volcanic outgassing or meteorite impacts that inject additional material into the vapor cloud. The planet is literally evaporating before our eyes. Mass loss rates are estimated at about 100,000 kilograms per second, roughly 1 ton per second material, stripped from the planet's surface and scattered into space. At this rate, the planet will completely disintegrate within about 200 million years, leaving only a cloud of orbiting dust, and perhaps a small iron core if the planet has one. We're witnessing a planet's final gasps, a dying world caught in the act of destruction. Following the discovery of KIC 125575448b, several similar objects have been found. K222b, mentioned earlier in the context of ultra-short period planets, shows similar transit variability caused by a dust tail. Observations reveal that the transits are asymmetric. The light curve shows a gradual ingress as the leading edge of the dust cloud begins blocking starlight, then a sharper egress as the planet and most of the tail pass by. This asymmetry directly traces the spatial distribution of dust around the planet, providing a kind of map of the disintegration process. But disappearing transits aren't always caused by dust. Some planets show transit timing variations, TTVs, so extreme that transits occasionally miss their predicted times entirely, appearing to vanish. Kepler 16b, the famous circumbinary planet orbiting 2 stars, exhibits strong TTVs. The gravitational pull of the 2 stars causes the planet's orbital plane to precess to rotate slowly like a wobbling top. This precession carries the orbital plane in and out of alignment with Earth's line of sight. When aligned, we see transits. When misaligned, the planet passes above or below the stellar disk from our perspective, and no transit occurs. Kepler 413b takes this to the extreme. This Neptune-sized planet orbits a pair of stars every 66 days, but its orbital plane precesses with a period of about 11 years. For several years, the planet transited regularly, producing dozens of observed transits. Then, as precession tilted the orbit out of alignment, the transits stopped. For several years, no transits were detected at all. The planet effectively disappeared from the transit data. Around 2020, the precession brought the orbit back into alignment, and transits resumed. This on-off behavior is precisely predicted by models of orbital precession in binary systems, confirming that we understand the dynamics correctly, but it creates observational challenges. If a transit survey observes a system like Kepler 413b during a non-transiting phase, it will miss the planet entirely. Conversely, if transits are detected briefly before precession carries the orbit out of alignment, follow-up observations years later might find no transits, creating confusion about whether the planet is real or was a false positive. Another cause of disappearing transits involves planetary rings. Saturn's rings are impressive, but they're small compared to the planet. They extend to only about 2.3 times Saturn's radius. If an exoplanet possessed rings far more extensive, say 5 to 10 times the planet's radius, those rings would block additional starlight during transits. If the rings are tilted relative to the orbit, the amount of starlight blocked varies depending on the ring orientation, creating transit depth variations. 1 SWASP J140747, 93 to 394,542, 6b, mercifully nicknamed J1407b, is a planet or brown dwarf with the largest ring system ever discovered. Observations in 2007 detected a complex multi-featured eclipse lasting 56 days as the object and its ring system transited a sun-like star. The light curve showed more than 20 distinct dips and eclipses, each corresponding to a different ring or gap in the ring system. The rings extend to at least 90 million kilometers from the central body, roughly 0.6 astronomical units, larger than Mercury's orbit. The ring system is so massive and extended that it blocks nearly all the star's light during the deepest part of the eclipse, a transit depth of nearly 100%, far deeper than any planetary transit. If the ring system orbits a planet, it represents a system utterly unlike anything in our solar system. The rings contain enough material to form several Earth-mass moons, and gaps in the rings suggest moons have already begun forming, carving out spaces through gravitational interactions. J1407b's orbital period is estimated at about 10 to 20 years, meaning the next transit won't occur until the 2020s or 2030s if it transits at all. If the ring system's orientation changes slightly between transits due to precession or other effects, the next transit might look completely different, or might not be detectable, creating another example of a disappearing transit caused by geometrical effects. Planets in triple star systems. Binary star systems are common. About half of all Sun-like stars exist in gravitationally bound pairs. Planets in binary systems face complex dynamics, orbiting one star, both stars, or being tugged between them. But some stellar systems don't stop at two stars. Triple star systems, where three stars orbit their common center of mass, are rarer but not uncommon, making up perhaps 10% of all stellar systems. The gravitational environment in a triple system is chaotic, with each star pulling on the others in constantly changing ways. Planets in such systems shouldn't survive the competing gravitational forces should destabilize orbits, ejecting planets or causing collisions within millions of years. Yet we've found planets in triple star systems, somehow maintaining stable orbits despite the gravitational chaos surrounding them. GJ667c is part of a triple star system located about 23 light-years from Earth. The system consists of two roughly Sun-like stars, GJ667a and b, orbiting each other at about 12 astronomical units, and a smaller red dwarf star, GJ667c times, orbiting the AB pair at about 230 astronomical units. GJ667c itself hosts at least 2 confirmed planets, and possibly as many as 7, including at least one in the star's habitable zone. The planets orbit the red dwarf at distances ranging from 0.05 to 1.2 astronomical units, far enough from the other 2 stars that their gravitational influence is weak but not negligible. The formation of planets around GJ667c is puzzling. The presence of the 2 nearby Sun-like stars should have disrupted the protoplanetary disk around the red dwarf, truncating it and reducing the amount of material available for planet formation. Despite this, multiple planets formed, suggesting that protoplanetary disks in multiple star systems can be more resilient than models predicted. Perhaps the disk around GJ667c formed during an earlier, more isolated phase before the current orbital configuration stabilized. Or perhaps disks in multiple systems develop protective structures, gaps, or rings that shield inner regions from external perturbations. Dynamical simulations of planets in triple systems reveal that stability depends critically on orbital separations and configurations. Hierarchical systems where 2 stars orbit each other closely and a third star orbits farther out can host stable planetary orbits, especially if the planet orbits the innermost pair, circumbinary, or the outermost single star, circumstellar. Non-hierarchical systems, where the 3 stars have comparable separations and masses, are far more chaotic and less likely to retain planets. The stability timescales can be short. Some triple systems show evidence of ongoing instability. One planet orbits today, but simulations suggest its orbit will destabilize within a few million years due to secular perturbations from the other stars. We might be observing the system during a brief window of apparent stability before gravitational chaos reasserts itself and ejects the planet. Kelt 4ab represents a particularly complex case. This hot Jupiter orbits a Sun-like star every 2.99 days. The host star is part of a hierarchical triple system. A close binary companion orbits at about 70 astronomical units, and that companion itself is a binary consisting of 2 white dwarfs orbiting each other at less than 1 astronomical unit. The planet orbits the single Sun-like star, far from the white dwarf binary, but the system's history is complex. The two white dwarfs were once larger stars that underwent red giant phases and shed their envelopes. This mass loss would have altered the gravitational potential of the entire system, potentially perturbing the planet's orbit. The fact that the planet survived two stellar evolution events, the transformation of two normal stars into white dwarfs, is remarkable. During the red giant phases, the expanding stars would have been luminous and massive, their gravity pulling on the planet from hundreds of astronomical units away. Yet the planet remained in orbit, apparently unaffected. Either its orbit is exceptionally stable, or it migrated to its current position after the white dwarfs formed, perhaps driven inward by interactions with a protoplanetary or debris disk that formed from material ejected during the stellar evolution. 16 Cygni is a triple system located about 70 light-years away, consisting of two sun-like stars, 16 Cygni A and B, orbiting each other at about 850 astronomical units, and a red dwarf, 16 Cygni C, orbiting at a much larger distance. 16 Cygni B hosts a gas giant planet, 16 Cygni BB, orbiting at 1.68 astronomical units, with an eccentricity of 0.68, one of the highest eccentricities known at the time of its discovery. In 1996, the high eccentricity likely resulted from perturbations by 16 Cygni A, which tugged on the planet over millions of years, gradually pumping up its eccentricity through the Kozai-Leadoff mechanism. This demonstrates how companion stars in multiple systems can reshape planetary orbits long after formation, even at 850 astronomical units, far enough that the stars are barely bound. The gravitational influence of the companion can drive significant orbital evolution. In closer triple systems, these effects would be stronger and faster, creating environments where planetary orbits evolve continuously, occasionally crossing stability boundaries and leading to ejection or collision. The search for planets in triple and higher multiplicity systems continues, but challenges abound. Stellar companions add noise to radial velocity measurements and can create false signals that mimic planetary orbits. Photometric transits become harder to interpret when stellar companions contribute light or create variable backgrounds. Direct imaging is complicated by the presence of multiple bright sources in the field. Despite these difficulties, dedicated surveys targeting multiple star systems have begun to map the boundaries of planetary stability, identifying the configurations that allow planets to survive and those that lead to destruction. Future missions like the European Space Agency's Plato will monitor millions of stars for transits, including many multiple star systems. Statistical analyses of detected planets will reveal how common planets are in binaries versus triples, and whether certain stellar configurations favour or inhibit planet formation. These observations will test models of disk dynamics, migration, and long-term stability, providing insights into how planets form and survive in the galaxy's most gravitationally complex environments.